In this lab, we will be determining an equilibrium constant, and we'll be using a technique called colorimetry. You'll mostly be learning about this through pictures and just descriptions. Obviously, this isn't an in-person lab. That would be ideal, but this is what you'll be doing in this lab and applying the concepts that you learned about equilibrium. So recapping on some major things that you've learned about equilibrium, some main things that we would have to remember for this lab, what equilibrium systems are. They are reversible reactions such as this one. This is just an example. And systems at equilibrium, the main definition of them is that the rates of the forward and reverse reaction, so rate forward, rate reverse right there, they're equal to each other. So they are both being produced in the same rate, so just as fast as each other. But in terms of concentration, that might be a little bit different. So here we can see a graph that shows us the rates, how they're first different, and once they reach equilibrium, they're the same. So that is in terms of rates of the two reactant and product. Now, as far as concentrations, you can see that once equilibrium is achieved, they have different concentrations, right? N2O4 is less than NO2, but they reach concentrations to which they can be constant at. So if that stays constant, this one stays constant. So overall equilibrium reactions are dynamic, they're not static. The rates of the forward reaction and reverse reaction are equal to each other, and the concentrations of products and reactants are constant. So what are we doing exactly in this lab? So we are using an equilibrium system. Now specifically, this equilibrium system is this one that we can see here, iron reacting with thiocyanate, and it's forming a complex called ferric thiocyanate or iron thiocyanate. So this complex, what's special about it is that whenever it is formed, you get a color change. So you can see here how as you begin first with iron solution, it's like lighter orange, goldish kind of, and the thiocyanate solution is clear. And then when you react the two and it starts reaching equilibrium, it will be a darker color. So this technique is, colorimetry, right? You're gauging how far the reaction has gone based off the color. Now you can actually measure this color, measure the intensity of it using something called a spectrophotometer. And in a few slides, I will show you what the actual data for this would look like, so you can get an idea of that. But overall, in terms of just visual, the more product, then the darker color that you will have. So main takeaway is that we are working with an equilibrium system, and then we can write out an equilibrium constant for this system, right? Our product divided by our reactants, and everything's 1-to-1, so nothing is raised to any exponents, everything's just raised to 1. So main takeaway so far. If you're curious about where I got this picture, it's from a YouTube video. You can actually go and watch this reaction happening if you want. That's, again, completely up to you. So far we have those main takeaways about just equilibrium in general. So what are we doing in this actual experiment? We are using spectrophotometry. I'm not going to say that word again. It's really hard for me to say. So you heard it once, there you go. But in part A, we're using this technique to develop a Beer's law plot of iron NCS. So this particular plot is what you see right here. We have concentration and absorbance on the y-axis. So basically, spectrophotometers, they measure something called absorbance. So you have like a little it's called a cuvette, but it's a little tiny like cup, right? A little container where you can put liquids in there, and it's like squared. It has a square shape if you look at it from the top. And what happens in spectrophotometers is that light will go in, and then a measurable amount of light, a certain amount of light, will go in and then light will be transmitted out. So think about whenever you have a cup of water or a cup of juice or anything, if you if you put like a flashlight next to it, the light will go through and then come out through, or you can see some of it flash out through the other side. And depending how dark the liquid is, so if it's water, you'll see a lot of the light, or it like spreads throughout. And then if it's like, I don't know, dark grape juice, you won't see that light come out. So you have different levels of absorbance of light depending on the substance. So you'll have different amounts of transmitted light, and then basically you can calculate something called absorbance depending on that substance. So because for us, we know that the darker the color of the solution, the more of the product we are forming. That is directly telling us that if we have more absorbance, we have a higher concentration. So we will get something like this, a like directly proportional linear relationship. So part A involves drawing this plot. A high concentration of iron that we are making in part A, and we'll get to the actual how we're making those solutions or how those solutions were made, right? Imagine that you did it. But in part A, we have a high concentration of iron, 3 plus. This will force the reaction in the forward direction until all of our thiocyanate is consumed. So the amount of our product, our complex, is limited by the amount of this. So we have this in excess basically, and then we have thiocyanate that is limiting, and then this, because this is limiting, this directly tells us how much product we will get. So the amount of product or complex is equal to our amount of thiocyanate. That's our limiting reactant. So in part A, we were making a standard plot that we will be using. And now in part B, we are making some different equilibrium mixtures. So we will be referring to that Beer's law plot in part A for certain information. So I'm being kind of vague here just because in the applied exercises, you actually go in depth and calculate a bunch of things. So if at this point you're looking at this and you're like, I don't know what's going on, that's okay. We're going to take it step by step in the applied exercises and data collection part. So overall procedure, I keep these very simple just because, you know, if this were an actual in-person lab, then we would be doing a procedure, right? Here we are using some data, interpreting it, calculating things. So we're getting that side of things, which is super useful, and applying concepts that we learned in lecture. So that's what we do here. In terms of what we're actually doing for this lab, first you're just going to do the usual research the MSDS for both reagents, fill in that table, read part A and B carefully to understand what exactly is going on, how everything was prepared, and then part 3, calculate information and answer follow-up questions in the applied exercises. Okay, so in the data that we have, as far as data collection, we have information already presented, and we have, I think, maybe a few more data already collected and presented, but I have it in the next sections because it's more relevant to that. But as far as this part 3 data collection, we have 2 different tables. We have our standard solutions prep data, and then we have our equilibrium mixtures prep data. So this standard solutions is what we did in part A. We made some standard solutions in order to make a Beer's, or to measure information for a Beer's law plot. So read this part carefully right here, what was done. Note especially your total volume, and also note what I mentioned about how our iron ion is very high in comparison to our thiocyanate because of what we're trying to do. We were trying to drive it to produce a lot of product, right? So read how they were prepared. And then same thing for part B, just note the total volume. This is important later on when we start calculating our concentrations of our, solutions that we are working with. Okay, so for our applied exercises, major thing to note, and I kind of put it out as this giant disclaimer here, to receive credit for this section, you either need to take a picture of your work or you can scan the work. But basically what I'm looking for is you showing all the steps for a sample calculation. What do I mean by sample calculation? A lot of these calculations are going to get repetitive, but all I want you to do is show me at least one of them. I don't care which one it is. Show me at least one of them from each, kind of major step from each table that you're doing. And that shows me you know how to do them. And then, you don't have to sit there and write a bunch of stuff, like a lot of calculations. So, because I know that's a lot. And that would just be busy work at that point because you're just repeating it over and over. So just show me a sample for each little section, for each table, and that will be enough. And make sure to show all your units, show everything. If something cancels out, show that. Okay, so here is where everything starts ramping up. For the applied exercises, we have about 3 major steps, I would say, or 3 major tables that we have to fill in. So this first table, and I'm not sure why I included this right here. This is on the next one. But anyway, so this first major step is part A and B on these step-by-step calculations. We are calculating the molar concentrations of our thiocyanate and our complex in each solution using the following information. Using the information in table 2. So table 2, that's back in our data. So just note where I'm telling you to get your information from and just go back there and take each major portion, like this one for example, take these one at a time. So if you're doing this major portion here, first, don't even look at everything else yet. It will just, you'll get overwhelmed. So don't look at anything else. Look exactly at what I'm telling you. So I'm telling you, go back to table 2 and use equation 4 to calculate all of these values here. And then you'll also report the concentration of our complex because we know that our thiocyanate ion is our limiting reactant and it's determining how much complex we're making. We can just set them equal to each other. So essentially you're just doing one calculation, right? You're figuring this out, and then whatever you get there, you will report for our complex as well, our iron thiocyanate complex. So you're using equation 4, information from table 2. Again, remember I told you to note or make a mental note in your head what the total volume that we were working with. It's stated in part A. Okay, so like I said, take one thing at a time. This is the first thing that you're tackling, and then we'll do the next 2. All right, this is our next major table that we're tackling. So here we are calculating the initial molar concentration of our thiocyanate and iron in each solution that we made in our equilibrium mixtures. So remember in part B we made equilibrium mixtures. They're not the standard mixtures. So there we mixed certain amounts of each solution. They each have their own concentrations. So we're using the information in table 3, that's from part B. And you're using equations 4 and 5. So 4, I just mentioned it in the previous portion, and then here is 5. So I just didn't want to copy and paste too many times. So that's what you'll be using. And then report everything here. And then notice that you're given some more data here. So this is coming from part A. Okay, so this is the last final portion that you're tackling. Calculate equilibrium concentration. So that first major portion was just finding out the standard concentrations. Second one, the one we just finished, was finding initial concentrations. And now we're finding equilibrium concentrations. So we are going to calculate our equilibrium molar concentrations using this information in the information from table 5. So table 5 was the one we just finished, that we just filled in. So you're going to go back to there. You're going to use whatever information you need from there in equations 2 and 3. So equations 2 and 3 are right here. Record below in table 6, and then you will calculate our equilibrium constant. Once you get all of these filled in, you will use information from this table itself and back in table 5, and plug everything into equation 1. So you're going to be doing some plugging and chugging for this last step where you're calculating the equilibrium constant. And then you'll average it and you'll report that average of our equilibrium constant. So the best tips overall that I can give you regarding this lab is take things one step at a time. Don't try to get ahead of yourself. Like right now, I'm trying to talk kind of fast, stumbling over myself. You're going to do the same thing if you look ahead, don't even do that. Like if you haven't finished one portion, don't try to go to the next one. It's all like in tandem, like in steps. So like I said, tackle each major portion, each major table in the applied exercises, one table at a time, and it'll all fall into place at the end. And then after all of that, you will answer these questions. So these are kind of similar to, honestly, exam questions. So hint, hint, like these would be some good exam questions to practice, or exam type questions to practice. Like, so take them seriously. I know like at the end, you're probably like, oh, I'm tired. I don't feel like doing any more work. But you know, really think about what I'm asking. They're pretty like relevant questions to both this lab and also equilibrium concepts in general. So just answer them in 2 to 3 sentences. I'm asking you to actually, incorporate what you have calculated and think about that relative to, some hypothetical situations that I'm giving you. So let me know if you have any questions. But like I said, main tip for this lab is take it one table at a time.